Welcome to Lab 2. This is called Instrumentation Part 1. First part of this lab will deal with the oscilloscope and the function generator. Function generator generates signals, waveforms, and they are either, as this, well, you can read this, but it's a sine wave or a square wave or a triangular wave. Let me turn this on. And so it comes up. This here is the frequency, and you have a coarse setting. We can change the frequency, and then a fine tuner. There's a lag time between when you turn one of these knobs and the frequency settles in. Let's turn on our oscilloscope, and there is it takes a few minutes perhaps for this to warm up. This is your cathode ray tube, the CRT tube, displaying this signal. This is at 2519 hertz, and I can dial this down to, let's say, 1,000. Whoops. $1,009. Well, okay, it's settling down to about 1,018, and now I'm going to twist it again a little bit on the fine tuner, and I'm getting closer to 1,000. Okay, or 1,000 hertz or 1 kilohertz, and you can see the display here. So we can display square waves, sine waves, or triangular waves. Let's go back to the square waves. This will be the assignment to show square waves from 1,000 to 10,000 kilohertz. I mean, 1,000 to 10,000 hertz, or 1 to 10 kilohertz. There are two scales on this. We, if you want to create a certain output as amplitude of these waves, you would move this knob here. Okay. But if you get to the point where you can't deliver any more current voltage than you want, this is the voltage signal, is the distance between these 2 points, peak to peak, and the period is the period of one cycle, that is to say from here to here, and you just have to count up these squares, multiply it by this factor on the knob here. And if you want to know the peak-to-peak voltage, you would have to count up these squares from this point to that point and multiply that number of divisions by the number on the knob. If you wanted to go to a different scale, I mean, once you turn this knob to as far as it will go, we're going to depress a minus 20 dB button here, and you can see we've gone off scale, and I can change the display here, and we can see the signal again. Now, what I did here was change the display, the amount that we zoomed in or zoomed out to look at the signal. I didn't change the signal. This changes the amplitude of the signal, and these knobs change the frequency. Okay. So now I wanted to remind you there's a lot of knobs here, but there are 4 knobs in this case that are variable, and we're not interested in making the signal appear variable. One is this one here, and it's labeled variable, but if I move it, you can see we change the signal or the display. But you can't make any measurements like that. So you've got to turn it all the way turn it clockwise till it clicks. This knob here, it's called, it says hold off, but if it's not in its position, you get something strange. And so I just move it till, rotate it till it clicks. Okay, yeah, counterclockwise in this case. These two knobs are the same way. They're variable for the voltage. If they're not in the click position, you can change the display. And this is the same way. This is for channel 2, which we don't have hooked up. What I have here is a BNC cable coming out of the function generator, the output, going into channel 1. And if I wanted to, I could send another one over here to channel 2. BNC cables are these items. They fit into here. That you have to line up the slots and give it a twist, and they're connected. And in this case, I have the ends of the connectors clipped to each other, red to red and black to black. And of course, you don't want them to touch each other and short out your circuit. But all the black or ground should be common, should be connected to each other. All right. So that's an introduction to this. If I want to look at channel 2, I could flip this over to channel 2, which, as I say, there's nothing there, and it's set on ground right now. And if I want to see both of them at the same time, I hit dual. But we're just interested in channel 1 right now. And this is ground. And if this were not positioned, you can position ground wherever you want, but I'm going to put it right in the middle and call that 0. And so I have an isometric display of my square wave. So in this lab here, as I say, you're going to take and dial in a certain frequency, and you're going to go from 1 kilohertz to 10. It doesn't matter if it's exactly 1 or 2 or 3. You just write down whatever this number is. Then you take and make this measurement. You count the number of squares, divisions from the top to the bottom of the display. And you can take and move this up and down to make it easier. Let's say I'm going to set that right there. And I can count 1, 2, 3, 4. And I'll call this 4.6 units, divisions. And I'll have to multiply that by whatever this thing is set at. Right now it's set at 5 volts per division. And so you would write that down. If I was working on that smaller scale, I would have, once again, I'd have something more in this reading. It looks like 4.4 divisions times 0.5 volts per division. Now, at the same time, I have here this meter hooked up to the same output. I have it clipped into the output, and I'm just going to take and look at the voltage reading on this. This comes up automatically reading DC. You push the mode button, it goes to AC. All right, and now you can see that is reading 1.0 volts and root mean squared. So this is that root mean squared that the write-up displays or discusses in one of the last pages of the Excel sheet. This is a similar meter, a little bit different. Okay, and you can see it has a slightly different output. And this is a much older meter. This is brand new, and this is probably a little cheaper design. And so you can see there's a difference in the output, and it's the quality that you paid for. Okay. I just want to point that out. One of the things you're going to be doing is using this to find the root mean squared value of this peak to peak value. Now, if this were a sine wave, we talked about how if you have peak to peak of a value of a sine wave and you half that, that is, say you get just the peak value, and then multiply that by 0.707, 0.7071, you should get the root mean squared value. And let me just manipulate this here so that I have see, I can move this like this, like that. But I want to increase the voltage, and it looks like it's it looks like the peak-to-peak value is 4 divisions times 0.5, or 2 volts per 2 volts peak-to-peak. Half of that is 1 volt peak-to-peak, and 1 times 0.707 is going to be 0.707, and you can see that I'm reading here a little less than 0.707, 0.683 volts root mean squared. And so you can see there's a difference. And once again, the quality of this machine is different from this. That's the point that we're making in this lab, is that these measuring devices are not equal. Some are more sophisticated, they're more expensive, and have a better output, better result.